Hello world. Today we're going to be going over doubly linked lists. So we are going to start with a quick overview of what a linked list is. If you're working with a doubly linked list, it's kind of assumed you've probably worked with a linked list before. Just to give a really quick reminder, a linked list is made up of these nodes, and each node has a data uh, value, so you can make that an int in this case. It could be any type you want. And it also has a pointer to its next. So that's a general linked list. If you keep track of the first element, you can access any other element within it by just iterating to that to node.next as many times as you need. So to get to the first element, you just take head.next. It's the second element, you take head.next.next, and so on and so forth. So we are going to go over the slightly more interesting sibling to linked lists, which are doubly linked lists. So the main difference between a singly linked list, which is also just known as a linked list, it's what we have right here, is the doubly linked list. So what makes it interesting is that it also has a pointer to the previous element. So that gives us a few benefits in terms of performance sometimes, depending on what exactly you're using it for. So that lets us iterate forwards and backwards. So if you have a doubly linked list, you might want to keep track of the head and the tail pointer, both. So the head is your first element in the list, and the tail is the last element in your list. So let's go ahead and make a simple list with 3 elements in it. Let's start with our head. Let's set the data to be 100. Let's give it some random number. Head dot previous equals null. So we want to set the same way that you'd set the next on your last node in the list to be null, sort of indicate you reach the end. You typically want to do the same with your previous node for the head, just to sort of indicate if you're iterating backwards that you've reached the end of the list. And it would be the responsibility of whoever's using the list to actually check for that. And then here we can say head.next equals new node. So now we can say head.next dot data equals 200. So this is going to be our second node in the list. Head.next dot previous equals head. So just to unwrap what we're doing here, we're taking head.next, which is our second node in the list, and we want to set its previous pointer, so this pointer here, to point back to the original head. Because if you look at head.next, the second element, the element that came before it, was the original head. So we want to make it so if you're at this element, the previous pointer does indeed point to the element that came before it. And we want to set head.next.next equal to a new node. And because in this case we're only going to make 3 elements of the list, this is also going to happen to be our tail element. So we can just say node tail equals head.next.next. And we want to, of course, set our the previous element equal to head.next in this case. So tail is pointing to our third element, head is pointing to our first element, and head.next is pointing to our second. So we want to set our third element's previous pointer to point to our second element here. And now this allows us to just go ahead and set tail.data, make it 300. So we're just going to be counting up 100, 200, 300. And tail.next, because it's our last element, we want to set it to null. So here we have our doubly linked lists, and no enclosing instance of type. What are you saying? Did I mistype something? This just came up right now. didn't it? No enclosing instance of type linked list traversal is accessible. Must qualify the allocation with an enclosing instance. Oh, there we go. That should fix it. Okay. Um, so yeah, so right now we have a doubly linked list with 3 elements in it. So let's iterate through it first a typical way, going from the front to the back, the way you would with a singly linked list, and then we'll try to flip that around. So we want to start off by setting our current node that we're going to use to iterate. We want to start at head, and then we can say while current is not null, we want to go through the list, and at each element we want to just print it out for now. That seems to be the right thing to do for these tutorials. In reality, you'd probably be doing something far more interesting than just printing out the values, but that's what we'll do for now. System.out.println. And after we're done processing it, in this case just printing, we want to set current to current.next. So instead of doing a println, let's just do a print here and then put a space between each of these. So we should expect this to print 100, 200, 300. And remember, close your curly braces, kids. All right, let's go. Errors exist. Why do you do this to me? Somewhere along the way, my curly braces got all messed up, but should be fine now. All right. There we go. So we have 100, 200, 300. But you could do that with a normal linked list. We never make use of the previous pointer here. So now let's do this again. Just copy and paste it. But now instead we want to iterate backwards. So in this case, we want to start with current set to tail, and we want to say instead of current.next, we want to say current.prev here, short for previous. Let's do a println to make it a little easier to read. So here we have it going backwards. So we had 100, 200, 300. Now we're iterating backwards from the tail, and now we have 300, 200, 100. So a couple things to point out. The first one is we could have replicated this behavior with our singly linked list. If we got creative, we could have, as we iterated through it, maybe used a stack and then pop elements off the stack as we did this. That would have required some extra memory. We could have also just gone through the list and printed out if our list is of length n, we could have printed out the n element, then the n minus 1th element, then the n minus 2 element. But that would have required going through the list n times, so that would have been an n squared operation. So with a doubly linked list, you become able to do that, to iterate through the list backwards without using any extra memory or taking any extra time. The only downside is, of course, you have to maintain this previous pointer, which we didn't have to worry about before, so that takes up a little bit of extra space, but it's normally not too big of an issue. So another common case where you might want to use this is if you have a list where you want to take elements off of the end of the list. So with a normal linked list, if you want to take an element off of the end of the list, so in this case our list is 100, 200, 300. So if we wanted to remove the element with 300 from the list, that would become a pretty annoying problem to solve, because we would need to iterate through the entire list, and then once we saw the element we wanted to take away, we'd have to remove that and change the next pointer on the previous element. And programmatically it's not that complex, but it would require iterating through the whole list. So if this is an operation that we're doing pretty often, that would typically not be desirable. But with a doubly linked list, we're keeping track of the tail pointer, And we also know, because we can iterate backwards, we know the thing that comes right before it. So what that allows us to do is it allows us to just remove that last element from the tail pointer. So let's say we want to remove our last element from the list. So all that we have to do is say tail dot previous. So this is our second to last element. Dot next equals null. So we're essentially taking the second to last element, so in this case one with a 200 in it, and we're saying make its next thing be null. And so now that means when we iterate forward, once we get to 200, we'll stop. And the only other thing we have to do is say tail dot, or tail equals tail dot previous. We have to update our tail pointer to now point to that 200. And that's really all it takes. This is a simple constant time operation. And now if we try to print it, we have, oh, I do that down here. That's smart. All right, so if we move the logic to actually print it down here, we should see just 100, 200, and then 200, 100. So we've removed the last element right here without actually needing to go through the entire list to do it, which for 3 elements isn't a big deal, but if you're dealing with thousands or even millions of elements, then that can become a very expensive operation. So by using a doubly linked list, we don't need to iterate through the entire list, saving us a good bit of time. So that's it for doubly linked lists. They are good to know, good to just have in your back pocket if you ever need them. And they're pretty simple too for the most part. It's a linked list just with a previous pointer. The main thing to keep an eye on is just to make sure that you update both previous and next whenever you need to. If you're used to working with singly linked lists, it's very easy to forget to update your previous pointer, especially when you add an element. You're used to just saying um, your current element dot next equals new node and then setting the data and then the next pointer to null. If you don't set the previous pointer, it's an easy mistake to miss because if you only iterate forwards, everything will still work pretty much perfectly. But if you iterate backwards and you forget to set your previous pointers, you will not have a good time. But yeah, that's it for doubly linked lists. Stay tuned for more. All right.